Hey, we're here with our kid from the shout-out land.
Yo, chemistry rocks!
All right, that would be Mr. Timothy Woods.
Yeah.
Sharing with this. And, of course, this is Mr. Bergman and...
Mr. Sam's the poet.
The poet?
Yes, remember I'm becoming a poet.
You are a poet and you didn't know it.
Okay, here's my lead poem.
Lead. Well,
Lead.
that's PB, isn't it?
Yes, you bring such pain, lead. Fired from a gun, you pierce flesh, deteriorating from many years of exposure. My hair, my skin, lead. Keeping Superman from seeing through. Lead, so heavy you are my burden. In my pipes and in my antique plates you haunt me, you weigh me down. Lead.
Oh, I like that. There's the
nice?
Superman. That's kind of like me, you know?
What?
I'm Superman.
Oh.
You didn't know I was Superman, huh?
No.
Well, you know, I kind of tried to keep it a secret.
Oh, okay.
Yeah, I knew that. So there's Superman.
All right. Well, I guess you do wear tights like he does.
I do wear tights. I do wear tights. Man in tights. I sometimes get strange looks. You know, I'm a cyclist. I'm in internet land. Yeah, okay, we just won't go there. All right, so we are going to start with talking about how to calculate strong acids and bases. So here we are, trying to find the right screenshot. There we go.
There it is.
Hey, strong acids. What's true about all strong acids, Mr. Sam?
100% dissociation.
You know, it's kind of like high school romances. What
It
happens
is.
to all
They
high school romances?
all break up.
Did you guys know that all high school romances break up? All of them? Don't.
Except for like the 0.001%.
Yeah, I think it's 0.001.
And that's about how it is with strong acids or so.
So it's actually kind of perfect here. So what we're trying to do is find what is the pH when you have nitric acid solution. Now, what do you know about nitric acid?
It's strong acid.
So if I had a strong acid, that's like HNO3, and it completely dissociates into H positives and nitrates. So this arrow right here, this arrow is in one direction. Hey, I love the music. How cool is that? Okay, rock and roll. Woo! Actually,
Yeah.
here's a good song. Rock and roll, it soothes the soul. I love this song.
Mm-hmm.
Days of old.
Can you tell we're doing this in the
That
middle of
old
school?
time of rock
today?
and rolls.
Those of you who are not our students, they do this 1 minute before class starts. We get to listen to some music.
Oh, I like this
So
song.
if you're our
Soothes the
student,
soul.
fast forward, about another 30 seconds or so, and the song will be over.
So, yeah, sorry about that, folks in internet land.
Did forget a negative sign on your nitrate, however.
Oh, I did, yes. So, all right, let's put a negative sign right
Yeah.
there. All right, music can end now. We'll wait. But
Anytime.
it does add some ambiance
It is.
to
It's nice.
I like this music.
Should I dance now?
That would be painful.
It would be quite
You
painful.
might fall and hurt yourself.
Yeah, I probably would.
Yes.
It's a good thing this isn't a video of me podcast.
That's true. They don't
that'd be
have to see
sad
our
and
ugly faces.
Hey, speak for
And
yourself.
now we're going to have like a beep, I'm sure.
There it is. Hey, okay, moving on.
Okay, so if you have a 0.10 molar solution of nitric acid,
After dissociation.
how much of this is going to go away? You can actually do like
we
an
can do like
ice
a little
table.
ice table or BCA table. Yeah, exactly. We're going to lose 0.1 and end up with
all
0.
of it goes away. And how much hydrogen?
All of it.
Well, it's 0.1.
Yep.
And actually, this
We
is
could do
0.1,
nitrate too, yeah.
but we don't care.
No.
Because it's asking for the pH. And
Yeah.
what is pH?
Negative log of concentration of hydrogen ions.
So that's the negative log of the concentration of the hydrogen ions.
Yep.
Well, that's just going to be the negative log of what?
0.1.
Now, do you need a calculator or something?
Not really, no, because 0.1 is 1 times 10 to the negative 1, and so that would mean my pH is 1.
Yeah. So pH on this one is very simple. It's 1. We didn't need a calculator on that one.
Nope.
Are we good or what?
Mm-hmm.
All right. Conversely, we can also do a solution. Now, actually, this is now a weak acid, though, right?
No, that's a strong.
Perchloric? Pardon me, it's perchloric acid. I knew that. I was testing you. Yeah.
I know.
So perchloric acid, you could do this, HClO4, and of course that also completely dissociates into hydrogen, and now the perchlorate, ClO4 negative. And so the hydrogen ion concentration, since it completely dissociates, is this number right here,
Yep.
1 times 10 to the minus 10th. So you would, of course, say that the hydrogen ion concentration would be what?
1 times 10 to the negative 10.
It would be equal to 1 times 10 to the
And
minus
if you take
10.
negative log of that, you get a pH of 10. Now that's kind of
pH
weird.
of 10. That should be the answer, right?
It should be, but
This is not true!
no, because that's an acid. You cannot have a pH greater than 7 if you have an acidic solution.
How do we do this, Mr. Sanders?
Well, we have to think about what the major species are in there. And if we think about the major species in our water, we have to remember that water self-ionizes. And that in pure water, the hydrogen concentration is 1 times 10 to the negative 7. Which is greater than 1 times 10 to the negative 10, meaning the water is acting as more of an acid than the perchloric acid.
So actually you would say that the hydrogen concentration would be equal to 1 times 10 to the minus 7th plus 1 times 10 to the minus 10.
Right.
There are two sources of hydrogen.
Yes.
The dissociation of the water, which is very rare that this becomes an issue.
Yeah.
And the dissociation of the perchloric acid that's very, very dilute. And so if you were to add these numbers, I bet I can do this in my head. It's about 1 times 10 to the minus 7.
Mm-hmm.
Because you see this 10 to the minus 10th number is infinitesimally small compared to the 10 to the minus 7.
Right. 10 to the third times smaller.
So the pH is
1,000
actually
times less.
very simply
Yep.
7.
Ding.
Not technically, it's actually 6.998 probably, or something very,
Probably.
very small. But for significant digits, actually I've messed up my significant digits. We would say 7.0 because we want to keep a 1 significant digit decimal after, as we talked about last time. Okay? Good. Hey, now let's talk about weak acids and weak bases. Now, with a weak acid, they have this thing called the equilibrium constant. The acid equilibrium constant, it's the Ka, and here are the values. Notice something about those values. What do you see about all those values, Mr. Sams?
They are all less than 1.
Yeah, they're all tiny numbers. The biggest number is 10 to the minus 2, and the smallest number is way down 10 to the minus 10. And this is, of course, not an exhaustive list of acids, but it's a partial list.
Yeah.
It's good enough. So now, when we work with these, we have to work with equilibrium constants, and so now let's work a problem. Hey, we have a...
That is not an equilibrium problem.
This is actually a not... Okay.
This problem right here.
Yeah, well, I guess we will...
We're
out of order. We're slightly out of order. This will come.
We should have checked the table about 2 slides later.
This is going to come a little bit later, but we'll talk about that. We did.
Put that in the back of your brain.
Put that in the back of your brain cells. All right, now we have 2 strong acids. We have nitric acid and we have hydrochloric acid. It's asking what's the pH of the resulting solution. This is a pretty tricky question, actually.
A little bit, but this is a good AP question too.
Yeah, AP class. We should probably have AP questions. Okay, so what we've got is we've got 2 strong acids. So what would be the molarity of this acid?
That one is 0.00125 molarity,
Sort of.
but we need to do an M1V1 equals M2V2 problem
Let's
because...
think this through. I've got 2 beakers. One's filled with nitric acid, and it's like 54 milliliters, right, from the problem. And another beaker is filled with hydrochloric acid, and I have 25 milliliters. But what I'm going to do is I'm going to pour them together into one beaker. Now, when you pour them together, we're going to have a mixture of 2 different strong acids. Well, when you do this, we're going to dilute the acid. So we have to use our equation M1V1 equals M2V2 to find the molarity of the final molarity, the M2, of each acid separately.
Yes.
So let's do the HNO3 first. So if I do the HNO3, M1 is 0.00125. That's my molarity, molar. That's M1. V1 is, how much did I have? 54?
54.
Well, now why can I use the volume in milliliters? Why don't I convert that to liters?
Well, we're going to add them together, and they're going to be in milliliters for your V2, so the units just cancel out.
So what's V2? It's going to be 25
79.
plus 54, 79. Now, folks, we got that by just adding the 2 volumes together. So the molarity of this acid is now 0.0079 molar. Just solving...
Sorry, the one above it.
Sorry. Okay.
That's for the next one.
Oh,
8.54 times 10 to the negative 4.
10 to the negative 4. Actually, 54. We can keep the 3 digits. I think.
Okay, and then we would do the same thing for the other acid, the hydrochloric acid, and the M1 is 0.025 molar times my volume, which was 25 milliliters, equals M2 times 79, again, because they're both in the same beaker.
Yep.
And so M2 is...
That one is 0.00791.
Now, what do we do next? That's just molarities.
2 molarities, but if we add them together, then that's our total concentration of hydrogen ions in this solution.
So it would be 8.54 times 10 to the minus 4th plus 0.00791, and that comes out to be 0.00876 molar. Now we're just going to take the negative log of this, and we get a pH of 2.0, I think 2 digits, probably because of the 54.
Yeah.
No, we have 3 digits. Look at the problem.
The volumes are all
20. No.
2
oh,
sig
there's
figs.
2. Yeah. Okay.
Yeah,
54 is the
2 sig
limiting.
figs.
So 2.06 is the pH.
Yep.
Okay.
And that makes sense because they're acids, and that's an acidic pH.
Yeah.
All right. One more. This one's a base.
Okay, so we have a base, sodium hydroxide, with 25 milliliters of 0.25 molar. So to find we can find the hydroxide concentration. Actually, we should make a note. This is sodium hydroxide. Sodium hydroxide completely dissociates into sodiums and hydroxides.
Because it's the strong base.
And he's like, all strong substances completely dissociate. Again, the old high school romances, they all break up. So the concentration of the sodium hydroxide is simply 0.25. 0.25.
Does that 25 milliliters do anything for us there, Mr. President?
You know, that's kind of a distractor, actually. Yeah, they don't need to know that. So
extraneous information.
Extraneous information. If I mixed it maybe in a diluted, that'd be a different thing.
Yeah.
So if you take the negative log of the hydroxide concentration, that's equal to the POH. I would do that first.
And that gives us 0.60.
0.6?
Yeah, 0.60.
602.
02, okay.
60. And that's equal to the POH. Now, how can I find the pH? The question says, what's the pH?
14 minus that, because pH and POH always add up to 14.
Actually, at 25 degrees Celsius,
Yeah.
Equals, 14. So you just have to take 14 minus 0.6. We could probably do that in our head.
13.40.
That'd be 13.40 equals the pH. And that is a basic solution, a greater pH than 7.
Yep.
So that makes sense.
Answer makes sense.
Totally.
Okay, now we're going to do weak acids.
Weak acids and weak bases. Okay, now, we had this conversation earlier. Guess what? There's this amazing table of them, and this tells you the percentage, or kind of like a percentage dissociation.
Yeah,
we'll talk about problems like that, how much they break apart. By the way, the higher the number, what would you say about the acid?
Stronger the acid.
So these are stronger acids, stronger
of the weak.
And these are weaker. They're all weak acids, but the strongest weak acid, at least on this table, is the hydrogen sulfate ion.
Yes.
Okay. So that's kind of where we're headed with this. Okay, now let's do a problem.
All right.
Now we have acetic acid.
Yes.
Now what is the formula of acetic acid?
Well, it comes from the acetate ion, so I'm going to start with an H, C2H3O2.
So acetate is C2H3O2 negative.
Yep.
So the word acid, of course, assumes the hydrogen ion. So we have acetic acid, which is HC2H3O2.
And that is a weak acid, so we do not have 100% dissociation.
How do you know it's weak?
Because it's not one of my 6 strongs.
6 or 6 strongs, yeah. All right. So we're going to now draw a double arrow.
Double arrow.
And we're going to write H positive plus the
So
acid.
we can't just take the negative log of the concentration here because not all of it dissociated. So this is where equilibrium comes into play.
Ice tables have resurfaced on the map. All right, so what do I know? I have 25 milliliters of a 0.25 molar solution. What's up with the 25 milliliter?
Again, nothing.
It's a distractor.
Distractor.
So this is 0.250. How much hydrogen would you have at the beginning?
0.
0 and 0. See,
well, we have it from water.
Yeah, but it's
so small compared to 0.250. We don't
so
need to
this
worry
is
about
going to
it.
diminish. Since this is 0, this reaction will shift. It's an equilibrium system to the right. So this will be minus X plus X plus X. And then we're going to get 0.250 minus X, X, and X. Now, there's something else that we need to know to solve this problem, Mr. Sams. What would that be?
We need to know the Ka value.
So I'm going to go back to our chart.
Yep.
Okay, you've got it just right there next to you.
Yeah, and I know this one.
I do too.
It's the same as
and
ammonia.
so if you find the acetic acid right here, his Ka is 1.8. So I'm going to write that down. The Ka is 1.8 times 10 to the minus 5. So now I can write that the Ka expression would be equal to the concentration of the hydrogen ion times the concentration of the acetate ion, products over reactants, divided by the concentration of the acetic acid. Now I'm simply going to plug in my values. I'm going to plug in the 0.25 minus X on the bottom, the X's on the top, and then the Ka right here. I'll recopy this. I know this is getting confusing. So I'm going to say